Welcome to installment 22 of writing a 6502 assembler in assembly language. And we're going to continue working on the expression parser today. And let's just go ahead and end there. I want to mention that I thought about this last night, and I'm going to change how this works. If you remember, the issue we had last time is that this thing is recursive. So when I call, for example, this or exp subroutine, it can call other subroutines like and exp, which could eventually come back and call or exp again. So we have to have some way to preserve the local variables that this subroutine needs, so that if by recursive calls or exp ends up calling itself, that we don't lose the value of those variables. And at the end of last installment, I was pushing everything on the stack here. And I've decided I'm not going to do that, at least not at this point. What I'm going to do instead is I'm going to have a separate variables for each of the different parts of the expression parsing code. So instead of having here x1 type, I'm going to have or type, and this will be the type of the expression. This will be the local variable, so to speak, for the or exp subroutine right here. And this can be or val. Okay, and then now instead of pushing all this stuff onto the stack, I'm going to go ahead and do what I actually originally had. Put this in or type. Put this in or val +1. Put this in or val like that. All right, now I call and exp, and whatever that returns, it returns an expr type, expr val. I'm going to take that and put it in or type. Or type and or val are the left-hand side. Let's go back to the grammar here. So this call to and exp is this part right here, and whatever it returns gets put into or type and or val, because that's going to be the left-hand side of this operator here. We have the or operator has a left-hand side here and a right-hand side here. So we're storing the left-hand side in the or type and or val variables. And now we're seeing, is there actually an or operator, right? And what happens is, if there's not, then what we're going to do is we're going to take whatever is in or val and or type and put it back into expr val and expr type, because that is what the expr type and expr val variables are always used to return the type and value of the subexpression from the current subroutine, in this case or exp. So actually this should be, I made a mistake here, this should be or val. All right, and here should be load or type, and store that in expr type. Okay, and basically we'll come back to this section every time we're finished with an or expression, whether or not it has their or operators or not. If there are, for example here, we'll go to an or expr, and we'll handle that, and then we're going to jump back up here to or exp 0, which will see if we have yet another or operator. And if we don't, we'll go ahead and take whatever's in or val and put it into expr val and return. So here's the case of the bitwise or operator. So here is this JSR index, is we're getting here, this one here, the right-hand side. Okay, and it returns its value also in expr val expr type, and that's why we have to move it here. We have to take what index produced here and move it into or type and or val, because otherwise when we come here and call index again, it would destroy the previous value. So we move it. All right, and now we're going to take the OR val, that is the result of this first AND exp, and we're going to OR it, bitwise OR it, with expr val, which is the result of the second AND exp. Okay? And we put that in X for just a moment, the result, the low byte. All right, and then we do the high byte, put that in Y for a moment. Load OR type. And I talked about this last time. Later there will be a far more complicated type combination, but for now it's either defined, which means that type is a 1, or it's undefined, type is 0. So ending them together gives us what we want, which is that if either of the two sides is undefined, then the type result of the combination is also undefined. And only if they are both defined is the result defined. So that's why the AND works here, the bitwise AND. Okay. So we're going to put this in OR type. We're going to put this things, once we've done this, we have to store these back. Actually, I don't even really need to do this. No TX. I can just store this directly in OR val. Okay, so we're building our combined type and value, and then we're putting the result of that combination into OR type and OR val. The reason being, of course, because that way this will be then, now that we've done the bitwise OR here and here, this becomes the left-hand side for another possible OR operator. So it needs to be in the OR type and OR val variables. And just for my own silly aesthetic reasons, I'm just going to change this around like this. Okay. All right, and then we go back up to OR exp0 to try to get another one. And then we have to do the same thing here. This is the case of an exclusive OR operator, right? So we'll load expr val, exclusive OR val, store OR val. Okay, load expr val plus 1, exclusive OR val plus 1, store back into OR val plus 1. All right, load expr type and OR type, store OR type. All right, so get rid of that stuff. Now we see both branches of this, the opexp1 branch and the opexp2 branch are basically identical. The only difference is that this one does exclusive OR and this one does inclusive OR. These two pieces of code could be combined if absolutely necessary by simply having a common piece of code and then altering the opcodes on the fly. But that's kind of ugly, and if we don't need to do it for reasons of lack of memory, then there's no point in doing that. So we'll leave it like that. Okay, good. So now the OR exp subroutine is basically what I want. And let's move on now to write the AND exp subroutine. And this is going to be almost identical to the OR exp subroutine. So I will go ahead and just do a copy and paste. All right, don't delete that because I want to keep that. Okay. So now that I have AND exp, and now I'm going to, if we just look at my grammar, this is going to call sum exp as its subroutine, sum exp. All right, so it's basically all going to be identical with only one small difference, which is that there are not now two different types of operators that we have to worry about. There's only one, bitwise and. Okay, and here we're going to use a separate variable called and type, and val, and val like that. And now we don't have, there are not, again, here we have the, for or we had two different operators that were a possibility. For this one, we have only one. The bitwise and operator is the only possibility. So we'll go to and exp1. This would be, of course, and exp0. All right, and we just basically have to change all of these ors to ands. Okay, and then here also. And then this calls not and exp, but sum exp. And like that. Oh, one more. Okay, so that is all done there, assuming I changed everything from or to and correctly. Okay, and now what we need here is new variables here. So we're avoiding the problem of, for example, using this variable in or exp subroutine and then destroying that variable by calling the and exp subroutine by having a separate variable. That's good as far as that goes, but of course if we could eventually have a recursion so that we would call or exp would call and exp, which calls sum exp, which calls mul exp, which calls unary exp, which calls term exp, which calls or exp again, then we will have to have a way to save the old value of or exp before we do this right here, and we will do that. What I'm going to do though is at that point, if we get to this point here, is I will simply put all of these things onto the stack and then make my recursive call. And for the time being, I'll put it onto the 6502 machine stack just for some testing purposes, but ultimately I think probably there should be a separate space. Well, what I'm going to do is I'm going to see how much we have to put on the stack. If when making our recursive call, we have to put, I don't know, let's say if it turns out to be 16 bytes on the stack, then that means we would have the ability, it probably would be fine to have 10 levels of recursion, which is almost certainly never going to happen. We can also, when doing that, check to make sure the stack isn't getting blown out by looking at the value of the stack pointer. And if it appears that it's about to get blown out, we can have a fatal error and say the expression is too complicated. So that's not really a problem. As long as we don't blow out the stack, we're fine. Okay, so the next thing is we have to do the sum exp. And it's going to be almost exactly like or exp, as you can see, only it has the plus and minus as our operators instead of these two here. Oh, well, I did forget one small thing here. This is actually doing a bitwise or, but it should be doing a bitwise and, because it's and. All right, well, that solved that problem. Let's go ahead and get that stuff that I copied out back. We can just do this again. There it comes back in again. Okay, sum exp. And sum exp is going to call mul exp. So here we have mul exp, and we have sum type, sum val, sum exp 0. And instead of these operators, we'll have these operators. And there will be two of them, sum x2, sum val. Sum val. All right, this is sum x1. This is for the plus operator. And this is again going to be mul exp. All right, and instead of, now here, what we have to do is we have to go ahead and set clearly carry and ADC sum val, right? See, we're adding. All right, and now the high byte, ADC sum val, sum val. So now we've added those two 16-bit values together. All right, combine the types in the same way. There's no difference there. All right, that looks good. Now we have the subtraction part. All right, and here we're going to have to set the carry. Okay, now this is a place where we can't, the order in which we do things is important because we're going to take this one here and subtract this one here, which means this one is the one called sum val, and this one's the one called expr val. So it is necessary here to do it this way. All right, we take sum val and then we subtract expr val and store the result in sum val. All right, in this one, it doesn't really matter. We don't have to, we can just do it like this. All right, all done. All done with that. You see there's kind of a pattern, and once we get the pattern down, it's actually pretty easy to do. Okay, the next one is mul exp, and it's exactly the same situation. The only special thing is now we have 5 possible operators. And I'm pretty sure these are TLSH and TRSH. All right, so let's go ahead and once again, we can bring that back in. All right. And mul exp is going to call unary exp. How many characters is that, by the way? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, although I've written here unary exp, I'm going to call it in the code just unexp like this. All right, mul type, mul val, and I don't want to forget. Right, so I'm going to go ahead and add these variables in here, right here. Like that. Okay, so we have or, and, sum, and mul. Just make sure, or, and, sum, mul. Yeah, that looks good. All right, get back up here and keep working on changing this one around. All right, mul exp 0. Okay, so now here, like I said, we have there were only 2 possibilities for or operators and 2 possibilities for sum operators, but now we have 5 possibilities for this here. And mul exp 1, mul exp 2. All right, mod. Mul exp 3. And what was it? TLSH. Mul exp 4 trsh mul x5, and that's it. So we have all the possibilities here: times, divide, mod, left shift, right shift, and which are here because they're basically also a way of multiplying and dividing, but just left shift is multiplied by 2 and right shift divide by 2. Otherwise, we're going to unscan, and we're going to take molval and return it as a result. Okay. All right, so the thing that's going to happen here is that I'm not actually going to do the multiplication at the moment because the 6502 does not have a multiplication instruction, and I will bring in some code previously written to do multiplication rather than, I've already written it a long time ago, and I'm not going to try just to, like repeat it just on the fly here. So I'll bring that in, but I'm not going to do it yet. Okay, so this is also going to call unexp, unary expression, just like here. Okay, so for the moment, if you have a multiply, I'm actually just going to, I think, do nothing, just leave it all alone. But I will, so in other words, this will just be deleted. Later there'll have to be a call to a multiplication routine here. All right. So here will be like insert call to multiplication subroutine. All right, and this here is the division part. And this also will be insert call to division subroutine. And of course, the division subroutine has a problem that you could divide by 0 and cause an error in that way. But that will just be another way that we can return an error from our parsing code, from our expression parsing code. Okay, and of course, if expression parsing, you also can have the problem that, for example, if you have an undefined symbol as part of your expression in the second pass, then that will be a problem too. In the second pass, everything has to be defined and the expression has to evaluate to an actual number, otherwise it will be an error. But let's get rid of this stuff for now. Oh, actually, I did mean to keep this part here. Yeah, actually you can see this is going to be the same in every branch, so we could actually just have some place that jumps to that does that for everybody. That would save a little bit of space, a few instructions. All right, and here is going to be insert call to division routine. But in this case, it's for the mod, that is the remainder. And I think I'll just go ahead and put here jump mul x6. And down here we'll have this code. And so I never bothered for the others, but because there were only 2 branches in the code, but here I'll just, because there's 5 branches in the code, it actually saves some space to do it this way. Okay. that last one. Mul exp6. This should be 6. So after it does the multiplication, it'll come down here and combine the types in this way. And actually, to be honest, that I just realized this is not going to work later on, because the way that we combine types will be far more complicated later on, and probably it might have to be different for different operators. But for now, it can stay this way. Okay, let us continue. All right, at this point, no, this is going to be the left shift, and we can actually do that. That's fine. It's easy to do a left shift. So what we're going to do is take the value that's in mul x, or mul val, and we're going to shift that left the number of times specified by x per val. And of course, if x per val has to be less than 16, otherwise, I mean, if it's more than 16, it's going to be shifted out to make a 0. So what we will do is take a quick look at x per val plus 1, and if it is not 0, then we'll go to mul exp for a, I'll say, and then we'll look at x per val. Actually, I can just go ahead and load it into x per val, into x, and compare x to 16, and if it's greater than or equal to 16, we'll also go to mul exp for a. So basically, if this test, if the number of places we're supposed to shift is 256 or greater, and this, assuming that it's not 256 or greater, we'll check and make sure that if it's 16 or greater. In either case, we go to mul exp for a, which will be down here in just a minute. Yeah. Okay, I'm going to change it to 5a, but you'll see why in a moment. So now we have to shift it left x times. So to start off, we should make sure that the carry doesn't matter, because it's going to always shift into 0. So we need to, you know what? Let's make this b. All right, so now mul exp for a, we'll say shift left mul val, and then rotate left mul val plus 1. What this does is this shifts this byte low, the low byte shifts it left 1 and puts what was the high bit into the carry flag, and then rotate left takes that carry flag and puts it into the low bit of this one and shifts everything up, and the high bit of this goes out into the carry flag again. But that's just going to be thrown away. That we'll never use that. Okay, so ASL ROL, that's how you do a multi-byte shift. And now we're going to decrement x. We have one issue that I didn't think of. Anyway, if x is not equal to 0, then we'll go to mul exp for a and do another shift. So we can only shift one bit at a time on 6502, so we'll just count the number of shifts that we need. And once we're done with this, we have our new value in mul val that we want. And so we can just jump to mul exp 0. Yeah. Oh, I'm sorry, jump to mul exp 6 for the time being down here. Okay, we have the issue that I just mentioned, that what if the shift count is 0? A shift count of 0 here since we don't check it, we'll end up shifting like 256 times, which we don't want to do. There's no point in doing that. So when we load the expr_val here, we'll just say, if it is equal to 0, we can just go to molexp6 right away. The reason being is that shifting something left 0 means don't touch it at all, right? So if the shift count turns out to be 0, we'll just go right down here and we're all done. Otherwise, we compare it to 16. If it's greater than or equal to 16, we go to molexp5b, which we haven't done yet. But if it's greater than 0 but less than 16, we'll go ahead and shift it that many times here, and then we're done. All right, so now we have molexp5, which is the right shift. And we just basically have the same issues here. molexp5b, if the shift count is 256 or greater, otherwise load x with the low byte of expr_val, that is the shift count. If it's 0, then branch to molexp6, because that means we're not going to shift anything at all. Otherwise, compare it to 16. If it's greater than or equal to 16, then we don't have to shift because the answer is just going to be 0. That's where we're going to with this molexp5. And then molexp5a will be the loop to shift this thing right. Here we had ASL, the low byte, and then RL, the high byte. Here we can have LSR, the high byte, and then ROR, the low byte. So this shifts the high byte one to the right, and whatever comes out of the low bit gets into the carry. This shifts the low byte to the right, and the high byte of this, the high bit of this, is filled with whatever is in the carry. All right, and decrement x. And if x is not equal to 0, go to molexp5. And once we're done with the loop, jump to molexp6 to be all done. And here comes molexp5b. This is the case where we have a 16-bit value which is being shifted by more than 16 bits, while 16 bits or more, which means it just becomes a 0. So we can just load a 0, store molval, molval plus 1. We don't actually have to do the shifting. I mean, if we did actually do the shifting, it would be 0 anyway, but why should we bother with that? If the shift count is greater than or equal to 16, we can just go ahead and store a 0 in there and be done with it. Okay, so we didn't actually implement the multiplication, division, and the mod operators because I haven't pulled that code in from outside yet, but we did implement the left shift and right shift operators. Okay, and now it's time for unexp. Here. Now this is different. This code is different now. Here we don't have a sub-expression routine to call first and then look for operator. Here we're just looking for an operator. So in this case, we may not need any of these special variables down here. Well, I'll figure that in a minute, whether we actually need these or not. But here, instead of calling, like up here, it's going to have to scroll up a bit. Instead of calling a subroutine like here we're calling unexp, right? Instead here we're just going to first call scan. And then we're going to see what we get back. And we're looking for one of these unary operators. Okay, plus, minus, and so on. All right. So we'll go to unexp1 for that, and minus, I'm just thinking, probably, actually, let's hold off on the plus. I think we may not need to actually, well, it will be implemented. The thing is, the unary plus at the beginning of something doesn't do anything, right? In other words, if I type plus 3, that's just the same as 3, right? So that can be handled in a way where we just recognize it, but then don't do nothing. Okay. On X3. X4. On X5. Okay, now these things are slightly problematic because these are actually only change the type of the value. And, well, that's not exactly true. But it kind of more or less changes the type of the value. And we have, as of right now, our types is just our type that we have is either defined or undefined. Well, to actually change the type to specify this is an 8-bit value rather than a 16-bit value is something we can do later, but we can give the effect of this, the effect of how this works right now without actually saying, okay, it's 8 bits rather than 16 bits. And we'll see that. Maybe I'll explain when I write the code in just a moment, okay? All right, and so here we might have a plus, right? And I just put that there for now. So on X1, now we have to go ahead and call term exp like that, and we get back the result in expr type expr val as usual. And since here this is the unary negative, we have to negate expr val, right? And I just do that by doing a 16-bit subtraction. So I'll load 0, subtract expr val, store expr val. This should be set carry, not clear carry. All right, load 0 again, subtract the high byte. All right, that will do it. Now, there's actually an alternate way we could negate it, but this is fine. All right, and then the types can be combined in the same way we did in the last one. We'll just jump to on X6, which will combine the types, at least for now. All right, on X2, all right, it's going to get, and now on X2 is the bitwise complement. All right, so we have to do that. That's not too hard. We just load an FF, exclusive OR. Okay. All right, on X3, again, term exp. All right, now what this one is this is the operator that takes a 16-bit value and removes the high bit. The high bit is set to 0. I mean, the high byte, sorry, is set to 0. Okay, so for example, if you had a number, a hexadecimal number like 1, 2, 3, 4, and you put this in front of it, the result is just going to be hexadecimal 34 or 0034 if you want to think of it that way. But actually, it's not only going to do this, it's going to set the type of the value to be an 8-bit type only. And the use for this is that, for example, if I don't personally recommend writing code like this, but if I were going to put code in zero page, or something in zero page, like we have the issue that we could, I don't know. I mean, actually, when you do something like this, right? Load from a zero page location, the assembler is going to know it's a zero page location and automatically generate the correct zero page addressing mode. But if you have some reason to force what is actually has a value less than 256, but you want to force the assembler to recognize that not as a 16-bit value less than 256, but an 8-bit value less than 256, you can use this operator to do that. But anyway, so here we are, JSR term exp, and then all we have to do is put a 0 for the moment. Just put a 0 in the high byte of x per val. Like I said, later we're also going to change the type so that the symbol recognizes this is supposed to be an 8-bit value. But for now, we'll put it here. Oh, another reason this might make sense is that the way this assembler is going to work is that if I want to insert some 16-bit value into my object code, I can just write it. That's it. That's all I have to do. In many assemblers, you have to do something like define word 1234 or define address 1234. But in this one, all you have to do is just put the number 1234. That's it. That will put a 16-bit value in your object code. But what if I want to have an 8-bit value in my object code? Well, if I go like this, if I say, C0, there arises a question. Should this be seen as a 16-bit value that just happens to have a value less than 256? Or should this be seen as an 8-bit value? What is the assembler going to do? And the way I've thought about it is that the assembler in this case would insert this as a 16-bit value, would insert 2 bytes into the object code. But if you do this, it will insert 1 byte into the object code because you're telling it, I want 1 byte only. Okay? And that's kind of the reason for this other operator here, this at operator here. This can force something to be 16 bytes if it's already considered to be 16 bits if it was already considered to be 8 bits. I hope I said bits the whole time, but I hope you understand me. We're talking about 16-bit versus 8-bit, not 16-byte versus 8-byte. Anyway, this does that. Alternatively, it's always a possibility I could say, hey, if you do this, it's going to insert as a single byte value, which maybe that's what I should do. I don't recall what it says in the documentation. The documentation says one thing or the other. If this is inserted as an 8-bit value normally, and you want to insert that as a 16-bit value, then you have to go like this. And then this is telling it, oh, it's supposed to be 16 bits. It's an address, for example. So that's really what we're getting at. That's the purpose of it for these things. And actually, now that I'm thinking about it, I think that's actually the way it says, what it says in the documentation and the way I want to do it. That this will be inserted by default as an 8-bit value. If you want it to be 16 bits, you'll have to do this. I believe that is, in fact, what the documentation says. I don't want to go dig it up right now, but I believe that's what it says. Anyway, so this is the low byte operator, this one here. All right, and once we've done that, we're done. And here we can JSR term exp. And of course, we might and maybe should go back and not have all these separate calls to term exp, but just do it one time. We just have to remember, well, I don't know, maybe we shouldn't, because we don't want to call term exp unless we know that we have a valid operator. So we have to have already checked all these things first. So I guess we're kind of, yeah, we have to call it separate times. All these have all these separate calls. Anyway, this is the high byte operator. So here what we're going to do is we're going to load the high byte and store it into the low byte. And now we'll clear the high byte. Like that. Okay. And then jump on X6. Yeah, at this point we could just jump here and do the same thing, but then I have to put a label here, and that's so annoying, so I'm not going to do that. Okay, term exp, move the high byte to the low byte, set the high byte 0, good. And on exp5 is make an 8-bit value a 16-bit value, and that's actually purely a type thing. So at the moment, there's nothing to do there. This is really only an issue of type. Change type from 8-bit to 16-bit. We'll have to do that later when we actually have the difference in those two things as far as types go. Okay, and then this type combination is going to be just a duplicate of this here. Oh, actually, no, I'm sorry, it's not going to be a duplicate of that because, right, we don't have two sides of an operator. This is a unary operator. So there's actually any type changes that have to be done will just be done in this code here. So we don't need to jump to onexp6, we just need to go to onexp0 the whole way. 0, 0, 0. Okay. Onexp0, onexp0. And on exp0 is it what? So for these guys here, for all of these binary operators, the 0 part actually oh, okay, I see it goes up here and scan. Yeah, actually that's right. This is the same thing. So actually, no, this is not an exp0. And actually, it can just jump back here, right here. So in other words, not on exp0, just go to onexp. Like that. That. All right. The reason being is that you could have multiple unary operators in a row. It's perfectly legal to have something like this, right? You have a minus operator and then a. So what this would do, the result of this would be to give you from 1, 2, 3, 4, you get 3, 4, and then you get minus 3, 4, which is whatever it is, right? Pull it up here. Right, so 3, 4, and it would be CC, FFCC. Okay, so right now this would then yield FFCC. Whereas if we had, this would be different. First it would do the minus, which would give us 1, 2, 3, 4, 2's complement. EDCC, whoops, wrong thing, EDCC, and then the low byte of that would just be CC. So anyway, we can have multiple unary operators, one after the other. That's why we go back up to onexp to see if we get another one. If we don't, and maybe this should go to, if we get a plus, we should go on exp0. If we don't, we're going to, of course, unscan the token that we got that's not something we were expecting here. And just to be sure, go up here, see how this one does it. Yeah, it unscans and then it copies that and returns. In this case, we don't have to copy anything because the value we want to return is already an expr type and expr val. So all we have to do is just return, right? And you see what we're doing is if we get a unary plus, no, that's not right. If we get a unary plus, we don't want to go here. We should just go back up to scan, right? Because maybe we'll get a plus and then a minus, or a plus and then a low byte, or a plus and then a high byte, or whatever. So that's going to go, whoop, that's correct. This is just going to go up here. If we get a plus, we're like, okay, we got a plus. We just go up here to see if we got something else because the plus doesn't actually change anything. Oh, actually this code is, this code is maybe wrong. Yeah. I'm just thinking. So suppose we had something like this in the source code. I don't know, just something like this. Minus bitwise complement foo. It could be bitwise complement minus, it doesn't matter. Just something like this. Okay, so what we do is we scan, we get the minus, then when we get the minus, we go here and we call the subroutine term exp. But I feel like we shouldn't be calling the subroutine term exp because we actually should be calling unexp recursively, right? We get the minus, we should call unexp recursively and see if we get another unary operator. If we do, right? So we would like get a minus, call unexp recursively, get the complement, call unexp recursively and say, aha, well, in this case, we did not get another operator. So we call term exp, and then it'll return the value of the symbol foo, which will then be complemented, and then return that, which will then be negated, and return that. So this grammar looks like, to me, it's wrong. So this should be unary op, unary exp, or term exp. So in other words, if you get a unary operator, then you then recursively call yourself unary exp. If you do not get a unary operator, you call term exp, like that. Yeah, that's how that should work, I believe. Okay, so we're going to scan and see if we get a unary operator. If we do get a unary operator, then what we're going to do, and let me just not worry about the plus for the moment. I was thinking about that again. All right, so if we get a negative, we're not going to call term exp. We're going to call unexp All right, and whatever it returns, we will then negate. We will negate it, and then we will not jump back up here again. We will just return the value of that. Okay. And now how about setting the type here? Negating something doesn't change the type. It's either defined or undefined, so we just return it. That looks fine. Of course, there may be type issues later on, but for now it's good. This is the bitwise complement. We're not going to call term exp, we're going to call unexp. We're going to bitwise complement what it returns. And then RTS, we're done. This is the low byte thing. Again, we're just going to call unexp recursively. All right, we're going to clear the high byte and return. There will have to be, or at least it probably will have to be set type appropriately. Like this is a to do, right? To do, set type appropriately. And here we call unexp and move the high byte to the low byte, clear the high byte. To do, set type appropriately. RTS. Okay. To do, change type from 8-bit to 16-bit. Here it's probably change type from 16-bit to 8-bit. But in any case, all right, and return. So we've got all those things handled. All right, if we get a plus, let's say branch of not equal to unexp 0. So this would be the plus case. The case of the plus, we're just going to jump. So basically what we want to do is just do JSR unexp, and then we don't have to do anything to it, so we can just RTS. But that means we can just jump to unexp, right? It's a recursive tail call, which is the same as a goto. Okay. Now we have the case here of we did not get any of these unary operators. So what we need to do is unscan whatever we did get, which is not a unary operator. So actually that goes here. Unexp 0. Okay. Here. Recursive tail call. Just to remind myself that that's why there's this jump unexp here. We're basically doing JSR unexp and then immediately return, which is just a recursive tail call, so we can just jump to it. This is the situation here where we did not get a unary operator. So didn't get unary operator. You guys have certainly noticed I don't put a whole lot of comments in my code because, to be honest, I'm writing this code for myself more than for other people to read, and I know what things I will well understand later on and which things I won't. And so I tend to write these comments like I'm doing right now when I think this might confuse me in the future. Okay, so if we don't get an unary operator, we're going to unscan whatever we did get. And we are going to jump to term exp. And it's the jump for the same reason here. I mean, this is not a recursive tail call in a sense, but it's a tail call because what we would do is do JSR term exp and then immediately RTS like that. But in that case, you might as well just jump to it. Okay, so if we didn't get unary operator, we unscan this stuff and we call term exp, and whatever it returns is the result of unexp, unary exp. All right, and then this part is when we handle the non-plus unary operators. So you see what happens if we get a plus, a unary plus sign, we don't actually do anything, we just accept it and say, okay, fine, we got it. Let's go and see if we have more unary operators. All right, now that we have done this, we have all these direct recursive calls. We have unexp here, and then we call unexp here. That means, actually, we don't actually have any local variables here, do we? Right, I was going to say we have to deal with local variables, but we don't have any local variables. So if we got, for example, I said just something like this, right? We say, okay, JSR scanned, we got a minus. So go to unexp, we go to unexp1, and it's just going to JSR unexp, which goes right up here, and it calls scan, and then it gets a bitwise complement operator, unexp2, so it goes here, and the first thing it does is JR unexp again, right, which does scan, and it gets a name, so no, and here it unscans the name, calls term exp, and term exp will return the value of this name, and then it returns to here, and it'll go ahead and do the bitwise complement, and a return, which then returns to here, and it will do the subtraction, and then return. Yeah, so that's fine. We don't have to save any variables. We don't have any. Good. All right, so that looks right. Now it looks correct. I mean, apart from this type stuff there. So now we are on term exp. And the first thing it's going to do is scan. And term exp is terminal expressions. That is, it's the end of this tree of expressions, except for that actually we can already recurse all the way back. But let's take care of these things first. All right, so we could have a number. That's kind of the first possibility here. Let's actually say if it's equal to a number, go to term exp1. And I'm going to go ahead and do term exp1 here. If it's a number, all we have to do is load the token value and store that into the expr-val. Right, and a number is defined. We know what the value is, so we can go ahead and load, put a 1 into expr type, which later on will be, the type will be set to something like absolute number. That is, say it's not an address or something. It's not the address of a piece of code. It's not a label. It's just a number. But for the moment, we only have defined and undefined as type, so we'll call it defined. It's an actual number here. It's not something unknown. And we return. That's it. Done. All right. If it's not a number, we have the name and the forward and the backward reference. So let's do the name first. Next. So if it's a name, we can branch to term exp2. All right, and here the token value is a pointer to the symbol table. And here I'm not going to use a 0-page pointer. Yeah, I don't have to do that. Here, I just call it 3. Why not? Plus 1. Just make sure expr type, expr val, yeah. Expr type comes first, expr val next, that's important. They're in the same order they are in the symbol table entry. First the type, then the value. That's necessary to know here. Okay. Yeah, it's literally getting kind of uglier and uglier, but I am going to try to avoid using the 0-page pointer here. Just because it's a pain to save it and restore it. So what I'm looking for, if I don't use a 0-page pointer, is I'm looking for term exp3 to be load ffff, comma x, and basically this is going to point to the symbol table. So the offsets for the type in the symbol table entry is 12, and the value is 13 or 14, which means I need to have here a 12 in x. So this is the pointer to the symbol table entry, and offset 12 is the offset of the type. And I need to store that now in expr type minus 12 x. So x starts as 12, so that we'll get the offset of 12 from the symbol table entry pointer, which will be the type, and store it into expr type minus 12 plus 12, which is just expr type. All right, and then decrement x, and not decrement x, but increment x, and compare x to 15. And if it's not 15 yet, then go to term x3. That is back here. So it'll load offsets 12, 13, and 14 from the symbol table entry and put them in expr type minus 12 plus 12, which is expr type right here. Expr type minus 12 plus 13, which is the low byte of this, and expr type minus 12 plus 14, which is the high byte of this here. So it'll copy the values from the symbol table here. And that's what we want. Okay. That just makes me think now, of course, the type of the thing in the symbol table, if the symbol has already been assigned a value, the type should be defined. If the symbol has not been assigned a value, the type should be undefined. So I might want to go up and check to make sure that I'm actually setting the type appropriately when I define it, but that will be for later. Okay, so we just take that value and put it here. Take the value from the symbol table and the type from the symbol table, put it there, and that's it, we're done. Okay, not so bad. All right, now a forward reference to a temporary label, a numeric label, and that's going to be quite similar Um, but what it's going to do is it's going to get now this information is going to be in the variables that we have. Is it here? It's in the other source file. All right. So let's quit this, save, and it's in here, right? That's just symbol table dumping, debugging stuff. Here. It's an NLF pointer and NLF offset. NLB pointer, NLB offset. So let's take a quick look. So if we get a forward label, it's going to look in those things and put okay, it's getting a pointer in 0 page. It's the toke value is the address of the toke value is the label, whether it's 0, 1 through 9. 0, 1, 2, 3, 5, 6, 7, 8, 9. Okay, it gets the F pointer put there. So it just gets the value of it and puts it in toke val. The value of that thing. It's all done for us. Okay, so we can just copy that in there. We can just copy the value from toke val. Yeah, we can just copy the value of toke val into exprval. So basically it's this same thing here. Here it's actually a number and here it's a label, but we've already gotten the value of the label, that is the address it refers to. The kind of issue I'm thinking in my mind right now is that the label could be undefined, right? And I don't think I accounted for that. So like, for example, if I had code like this, like imagine this is the beginning of my source file right here, and I have load 1B, and here I have, you know, a label like, okay. The thing here is that there is no, if this is the beginning of the source file, there is no 1B, it's undefined. And that really only matters for the type purposes, but I don't think I actually accounted for that in my code that found those labels, because, and actually this is, in the first pass, it's definitely an issue. In the first pass, every forward reference is undefined, because a forward reference means it's it refers to a line of code that you haven't seen yet. And that's fine. It doesn't hurt anything that it's undefined, but it is. So, but I don't think I have to worry about that here. It's something I have to go back into the other source file and worry about there, whether or not it's defined or not. But I need to have from these things not only the token, not only the value of the symbol, I need to know whether it's defined or not. And the reason for that is because in the first pass, it's fine to have an undefined label, numeric or non-numeric, temporary or non-temporary. it's not finding the second pass. So I have to know if you've referred to an undefined label in the second pass. So the type is required. So I can do load tokeval store into experval, tokeval +1, store experval +1, RTS. But I need a type. So the other code has to also give me a type. Now, numeric labels can be only of two possible types. They can be the type of undefined, because you're referring to a numeric label that does not exist, or they can be defined. It's a label of some piece of code or piece of data. It's an address in your program. So the number of types you can have is very limited. It's undefined or not undefined, basically, but I need to know what it is. So if that other code puts in there, okay, it puts the value of the label into tokeval, it also needs to put the type of the value that is undefined or not somewhere. And I'm not sure I have a place for that yet. Another possibility would be to, well, so basically that was in the scanner. Yeah, I think it's best to do that in the scanner, but there's going to have to be some variable that gives me the type of the numeric label. And I think I just don't have that right now. Oh, I could always put it like in the text buffer. That's so hacky, but it would work. Like in the buffer that's at hex 200, used to accumulate strings and symbols and stuff like that, the text for those things. I mean, it's available. It wouldn't conflict with anything. Unless perhaps you had a strange situation where you wanted to get a token which turned out to be a string, and then you get another token which turned out to be, no, you get a for label, and then you end up wanting to get a string and put that back, and I don't know. I think I'm just going to have some other little variable for that purpose. Like in lab type, store then expert type. And this will work for both the forward and backward references. That is all the same as far as that goes. In fact, it's not even clear to me that I really need to have two different tokens for that. But maybe that's an optimization step I can work on later on. Okay. So anyway, later I'm going to have to do something like this. And that means that code that I just looked at in the other file will have to be altered. You know what I'm going to do is, for now, I'm just going to take it out and put a to do. To do. Undefined or defined. Okay. And honestly, I have no idea if the label is, if the type would be defined or undefined now. So let's just don't worry about it. Just skip it. All right, and now we have the last type of terminal expression, which is this one here, where if we get a parenthesis, we go and recursively call or-exp. Okay, and if it is that, then we go to term exp5. And otherwise, we're going to, if it's not, oh, sorry, not a right parenthesis, I mean a left parenthesis, has to be like that. If it's not a left parenthesis, we're going to unscan it, and we're going to have a syntax error, basically. There's some kind of error. All right, and I'll just put a return there. This is, again, to do. Syntax error. Parse error. All right, term exp5. And here is where we're going to have our recursive call to or exp. And after that, we're going to scan. And we are going to see if we get a right parenthesis. If we do not, we're going to go up here. Syntax error. If we do get a right parenthesis, then we're good, we're done. All right. But there's a little bit more work to do here. And that is that here is the place where we have to push all this stuff on the stack. I have 1, we have 3, 6, 9, 12. Fortunately, it's only 12 bytes we have to push in the stack. That is nice. Only 12 bytes have to be pushed. Okay. Load x0. Term x6. Load or type x. Push it. I guess it doesn't matter. I have to push it in the opposite order that I pull it, so we'll just do it this way here. Okay. Increment x, compare x to 12. If it's not, then go to term exp6. So this pushing 12 bytes starting right here, right? 1, 3, 4, 6, 5, 8, 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those 12 bytes get pushed. All right, then we call or exp. And after we call this, we should go ahead and retrieve those bytes off the stack. So now we're going to load x12. Term x7. We have to get them back in the opposite order that we got them. That's why we have a 12 here now. No, sorry. Get from the stack, store in or type x, decrement x. If it's not negative, if it's positive or 0, go to term exp7. All right. So when we get here, right, first thing we have to do is push all of these things on the stack because we're making a recursive callback to or type, to or exp. So load x0, get a byte, push it, increment. If we've pushed 12 already, we're done. Otherwise, go push another. Then recursively call or exp. After we're done that, we have to now pull them back in the opposite, put them in the opposite order. So we put 12 here instead of 0, get a byte, store it. Oh, actually 12 is wrong, 11 is correct. And decrement x, if x is not negative, then we'll go back up here. JSR scan just to make sure we get this right parenthesis. If we don't, then it's a syntax error. That's where that goes. Otherwise, we return, we're good. Okay, and there's one other thing we can do to check to make sure we're not going to blow out the stack. It's probably a good idea to do that. We can actually do that here. Okay, we can move the stack pointer to x. We can compare this with, we just have to make sure that we're not going to, the stack starts at a high value like FF, and then as you push things on, it gets lower and lower and lower and lower. So as long as we don't wrap back around to FF, we're good. So let's compare x to well, we're going to need 12 bytes to shove all this stuff on the stack, plus we're going to need 2 bytes for to call or exp, and then we're going to need more bytes to do any recursive calls there. So let's just think of 12 bytes for that, plus how many of those are recursive calls? 1, 2, 3, 4, 5, 6 levels of recursive calls till we get back to term exp. 6 times 2 is 12, plus 12. So we need at least 24 bytes on the stack available. And I'm just going to compare, kind of for my own sanity's sake, I'm going to make sure there are 32 bytes available. Okay? If there have to, compare x to 32, there have to be at least 32 bytes available in the stack. Like I said, the exact number is probably 24, but just to make sure I'm not screwing something up, I'm going to make sure there's 32 bytes in the stack available. If there are not 32 bytes of stack on available on the stack, then I will go to term exp8, I believe will be the correct one, down here somewhere. Otherwise, everything's cool, and I'll go ahead and do what I was just doing. Term exp8 is going to be an error, which is basically, big screw up because of your expression is too complicated. You've blown out the stack. Okay, so, and this makes me think that we're going to have to handle errors in a slightly different way as well. Because what we're going to have to do is have I'll have a variable called x_stack. See, when we get a syntax error, we're going to kind of propagate that error back out of all of these recursive calls, all of these subroutine calls. But this error that we've blown out the stack is not going to be handled that way. Instead, way up here, and this is why, this is exactly why I never made the subroutine expert just cause JSR or exp, and the recursive call goes back to or exp. I did not make the recursive call back here. I could have just called this or exp, but I had this feeling that that would not be a good idea. And now I see it definitely isn't a good idea, because what I need to do here is I need to save the stack pointer at the point where you call expr. I'll save the stack pointer. All right, and then I will call or_exp and return. All right, and then down here, if you get a blow out the stack error, we're going to just undo this entire chain of subroutine calls by loading this value that was saved back in there and putting it back in the stack pointer. Right? So that way up at the top there, the expr subroutine saves the stack pointer just after expr has been called in this variable. I'm going to load it back in there. So at this point, we can return, and we'll be returning from that expr call. So anything that happened in between there, how we blew out the stack, is just undone. And there's another issue with the way I'm handling errors, though, because right now, I think when I throw an error, I do like a jump to error, but that's in the scanner. This is a parser error, which is going to have to be handled slightly differently. Because in the scanner, if I get an error, I jump to error, and it just basically consumes tokens until I get to the end of statement, and then it continues from there. But this is a different situation. I need to print out a message. Right? Which is I could call it complex error. So, and this is actually not so good. The other error message, I think I might need a separate routine called p error for parse error. In other words, it's going to print this out. Then I do RTS here, and this RTS, actually I could just do a jump probably, because JSR followed by RTS is just jump. But it's going to be different than the error message, the error routine I have before, because this is actually going to, when I call this, it's going to return from expr. And it's printed out a message, it's counted the error, but the effect has to be the same as just saying that, okay, we returned from expr and there was a parse error in there. Something was not right in the expression parser. Well, that'll be something to worry about in the future. I mean, you know, like next installment or the one after that. So complex error is going to be expression too complex. And all this really means is you blew out the stack by having too many recursive calls in there. Okay, and I'll jump to p error, which I'm going to write in here right now real quick, although it may not actually be like this at all. I'll make that an entry. And this is just going to print the error out. And it's going to increment number error. I don't remember what it is. Is it in errors? And then return. But there has to be some way, and we haven't worked on the other syntax errors, there has to be some way that when we return from our parser, our expression parser, that we indicate, okay, there's an error, and therefore the rest of the parser has to be aware of that. I already mentioned up here, there's this syntax error right here. All right, and real quick before we finish this installment, I'm just going to go back to AS0, I think it is, and look for this error routine. Here it is. Yeah, it calls puts. Oh, okay, yeah, it prints this whole message out. So yeah, that's not gonna work. What I just did. Oh, in error it is. Okay. Okay. Yeah, and then this whole thing where it ungets a character and it scans. Well, I have to remind myself as to exactly how this thing works, and then we'll see if it can be used. So actually, what I'll do right now is get rid of this and just call this jump error, although I think this has got to change. Anyway, besides handling errors, we've got the entire expression parser written. Whether it works or not, I don't know, but it looks right to me. So that will definitely be it for now. And next time we'll work on trying to get this whole error handling done. And at that point, we'll be at a position where finally we can maybe actually try to execute some of this code and see that it works properly or not and fix it and make it work. So until then.